Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Good afternoon, everyone. Welcome to the Visual Analytics workshop. The major goal of this workshop are threefold. First, we want to bring together the recognized leader in this area to share their successful stories and rich experience in designing effective visual analytics systems to the e-science-related applications. Second, we want to demonstrate the typical use cases to facilitate scientific discovery and decision-making. And finally, we want to provide guidance and suggestion to the future work. So we include 3 talks in this workshop. The first talk is given by Professor Daniel Kam, and he will talk about how to solve real-world problems with visual analytics technology and its role in big data analytics. And the second talk is given by Professor Klaus Müller. He will talk about visual analytics of the high-dimensional data. And the last talk is given by Professor Huamin Qu. Huamin will talk about visual analytics of social medias. First, we invite and welcome Professor Daniel Kam to give his talk.
Yes, thank you very much for the introduction. It's a pleasure for me to be here and speak about the topic solving problems with visual analytics, the role of visualization and analytics in exploring big data. And if I'm talking to people, what is solving problems? What does it mean? What kind of problems? If I talk to my son, who is 19 years old, the main problem that he has is about soccer. He wants his favorite soccer club to win. But we won't be talking about these types of problems here. Maybe a more serious problem is earthquakes. And this is actually a very interesting and very nice example, not talking that much about big data yet. But if you look at the recent earthquake in Japan, and just plot all the earthquakes that happened before the big one that we had in Fukushima, and you saw and color it, the more dark it is in red, the higher the score was. Then you see that it wasn't that unlikely that where these little crosses, that this earthquake happened at this position. So it wasn't really unlikely if you just look at it. And if you visualize what is affected by an earthquake at that position, you see the coastline that is affected, and you can even simulate how it distributes over the Pacific Ocean. So you see where the impact is biggest and so on and so forth. So we see already how visualization can help us to understand these problems. But some of it is not really big data. So what are the grand challenge problems? And I found this page from the National Academy of Engineering, and they mention all the big problems of the world, the grand challenge problems. And if you look at these things, then you immediately recognize that all these problems, and you see there's everything out there that is a big problem. Financial, ecology, then you have energy, water, cyberspace, all these things. And they are all related, if you look at them, all related to big and complex data sets. And this is the first important thing to note. We need to deal with big data sets in order to make any solution. Now, the topic of my talk is about what can visualization and analytics help here. And the visualization of big data is difficult. That's actually bad news. We have about 1 million, maybe 10 million pixels on our screens. So if we deal with really big data, like hundreds of billions of records, we can't really visualize it all. At least there is no simple, easy solution to it. And that's actually kind of a problem. And if we try to scale it, and we have developed a number of visualizations, like here's a big tree map of network data, you don't see the important data in here. There is some red dots in here that are hard to perceive. And you can put this up on power walls, and this is like, again, network security data. And then you see, like, this is now the 100 most important ports where we had attacks on our network. And you can basically look at them. It's 1 week of data, 100 ports out of 65,000 ports. There's plenty of other data that we can't show, even if you have the big screen. And what you see here is basically, like if I zoom in, you see this development, and there are interesting things that you can see, like this is a backup process over the weekend that happens here. These are interesting things that happen in the middle of the week. There's something that's running in the beginning of the week, and this is kind of normal traffic here, where you have basically during the day more traffic than at night. So this is actually a nice example of a scalable visualization, but it doesn't scale to the extent that we need it to. So I do have some good news after that bad news about the visual part. Automated analysis of big data works, and it's usually scalable, at least most of it. So you can deal with billions of records, that's fine. And when should we use it? I think we should use it whenever possible. Whenever you can use automated analysis, it's a good idea to do. And the question is why? Of course, because it's cheaper, faster, more scalable, and less erroneous. If you put humans in the loop, it usually causes errors that computers don't do. So am I really telling you that we should get rid of the user? Must be some other thing that is coming. And if you look closely in any of these problems that I mentioned in the beginning, it's actually, I have to restrict this good news, the automated analysis of big data only works under certain preconditions. And what are these preconditions? I'll get to that in a second. The bad news is actually for automated analysis that these preconditions are really rarely met in real world applications. What are these preconditions? The preconditions are the data must be clearly structured, the semantics must be well defined, the data must be complete, correct, and not changing over time. And if you think of any of the data sets that I mentioned, it's usually not the case. Take molecular biology. Oh, the data is not clearly structured. The semantics is not clearly defined. Data isn't complete, correct, and it's changing over time. So it's all these parameters are not given. And one more point that is even more important, the problem is not well defined. We don't know what we are looking for. If we knew, then it may be easy. If you know the virus that you want to detect, you can write an algorithm that does it. If you don't know the virus, how should you? How can you write and there is no algorithm that detects a new virus that you don't know how it's defined, how it's working. And this is what people are doing at Symantec and other companies. They are updating the virus definitions every day. That's why we download the new definitions every day. Maybe you don't recognize it, but your computer, if your virus program installed, is downloading new definitions every day because they detect new viruses and tell your computer how to find them. But somebody has to detect it and distinguish between a new computer game and the virus. So this is kind of the problem well defined is really a problem, and this is true for many applications. Molecular biology, you don't know what you're looking for. If you knew the reason for the illness, you're done, right? The main part is to define the problem, and well-defined problems are often not the case. If we know how things work together for climate change, then we are done. But this is not well-defined. We have to discover this. And discovering can't be done by automated methods alone. And this is basically all the cases when automated analysis is not enough. It's basically the inverse to the preconditions that I just mentioned. I already mentioned some examples. Let me briefly go through a few of them. Network security. The data is IP flows. And if you want to detect novel viruses, as I already mentioned, there is no way to do it fully automatically. You can have systems that give you interesting data like effects that are sticking out, that are new. You can have algorithms doing that, but deciding on a virus or not can't be done fully automatically. You need the human because the problem is not well defined. Fraud detection, credit card or phone call data. I personally have worked with phone call data and credit card data both. And the thing is the same. You can have algorithms that highlight changes. You can have algorithms that help you detect potential fraud, but you can't decide on it without having a human involved. Otherwise, you shut down systems before you need to and have unpleasant situations happening for your customers. So the detection of fraud is still something where you need the human finally making the decision. Business analytics, customer feedback data, and I'll get back to that later if I have time. It's a real-time problem detection, what is kind of happening in real time. You get all this customer feedback from your customers, and you have to detect new things, not the things that you already know. And deciding these is again a problem where you need the human to be involved to prioritize and help. Molecular biology, I already mentioned it. If you have patient DNA records and want to find out about the root causes for an illness, this is something where you again need automated analysis, lots of automated analysis, but you need the human with the human knowledge and intuition. So what is visualization needed for? It's needed for interactive problem specification. So the human puts in the problem in the process of dealing with the visualization. And of course for interactive data exploration and understanding. But in addition, you need steering the automated algorithm to help the algorithm do the thing in the best possible way that you need it to do it. And you need to communicate the results. So we have different uses of visualization. And this is basically motivating what visual analytics is. And I've found a nice quote which is attributed to a very well-known person who probably never said it. It's attributed to Albert Einstein, but I don't think he ever said it. But who cares? Everybody attributes it to him. Computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. Together they are powerful beyond imagination. And this is the motivation and I would say even the best definition of what visual analytics is all about. Very nice sentence. And I don't think he said it because computers weren't that fast when he lived and was saying this supposedly. So I guess somebody attributed it to him. So what is visual analytics? It's a tight integration of visual and automated data analysis methods for information exploration and decision support. And what you see down here is a very simplified version. You have the data on one side and knowledge on the other side. And you see you can go from data to visualizations, from data to models by automated analysis. And the important part is you can iterate between the two. You can go back and forth between the two until you find what you need. And we rarely see that these days, but we need it urgently for many applications. And basically, the whole motivation is you want to bring in the abilities of humans and computers, where humans are good and computers are good. And this picture is actually quite old. I found it in a book about 20 years ago. And it's almost still correct. I put in the errors. This wasn't in there. And it's a nonlinear scale, of course. Computing power is incredibly fast now for computers. Data storage is beyond imagination. But if we look down here, modeling general knowledge on the computer is still something that we are struggling with. Real general knowledge of a 15-year-old child, bringing that to the computer is really hard. And you see that even with all the successes that IBM Watson had, some of these answers were really bad. Of course, some of it was great, but some of it was quite bad, and everybody knew in the audience that the computer was doing, because they don't have general knowledge. They do statistics, basically. Perception, we are still better, and creativity, I have no idea how computers, how even to define what creativity of a computer means. Like inventing relativity theory by computer, something we couldn't imagine. Writing music that Bach or other musicians did, I don't think we can imagine computers doing similar things of that degree, or paintings or whatever. defining what creativity means is even a problem here. So I believe we should combine these two things. And if you want to know more about what visual analytics is, we have I've coordinated a European program, a big program, and this was the outcome. This was a roadmap for visual analytics, outcome of the WIS Master project. If you want to download the book, just go to this webpage and have a look. You can download it from there. And it's outlining the challenges of this emerging and quite important field, how to bring visualization and analytics together for solving the real problems of the world, at least some of them. And I brought you a little video clip that we also generated that is motivating visual analytics and play a little bit of it. And this was also an outcome of the WIS Master project.
Biologists every day collect large quantities of data from wet lab experiments and high-throughput genome sequences. Data is overwhelming. Nobody knows how to explore it. In the business intelligence domain, part of the work consists in analyzing all the news data concerning companies who want to optimize their strategy. They need real-time analysis tools to stay ahead of the competition. Banks serve billions of credit card transactions per day. They have to quickly detect how criminals are acting in order to neutralize them. If criminals are quicker than the banks, you lose your money and the banks lose your trust. In case of epidemics, finding the cause of the disease involves a large amount of data from several areas and supports. Experts have to deal with multiple sources of information, a huge number of entries in each, and waste time to cross-combine them because of lack of support and no way to query the data efficiently. But what do these examples have in common? All these people encounter the same problems. They have to deal with masses of dynamic data. They want to answer a lot of questions, sometimes unclear questions that require exploration. They need both computational analysis and interactive visualization. And they need to export easy-to-understand representations of their results for communication. Let's now imagine the epidemiologist with visual analytics capabilities. Here we have an epidemic that touches 4 countries with an abnormal hospital admission rate for people with the same symptoms. They can share their own database of hospitals concerned by the disease and visualize them on a map. It looks like it is not contagious, but experts need further exploration to identify the causes and the nature of the epidemic. After hospitals, a new idea is to share and visualize the localization of people concerned by the disease. Looking at the propagation of the illness, we can see that the pattern doesn't follow communication axes or circle waves. This is a specific pattern that has grown and stopped abruptly. Experts therefore conclude that it is not a contagious disease, but most probably a food poisoning. So epidemiologists decide to investigate what kind of products all of the patients have ingested and localize them on the map. First thing to do, identify the 3 supermarkets closest to these people. Now, with a list of the supermarkets that might be involved, they can immediately take a look at all the products most of them have in common. This time, the list of products is too broad, and they immediately know that they have to try something else. The experts then try examining the local suppliers and distributors.
I think I'll stop here and if you want to see the rest of the video, and it's going on for a few more minutes, it's on YouTube. Just type in Vismaster and you'll find it. So this is kind of just motivating visual analytics. And I hope you have now seen that this is an example, fictitious example of how visual analytics may work. This is not operational. And this is true for many reasons. This is the case for many reasons because you don't have the data sources for such an example ready from multiple countries and so on and so forth. But people also don't have the tools to explore that data, analyze and visualize it. What I'm going to do now is, after explaining a little bit about the role of visualization analytics, I will provide a few examples how visual analytics may help. And I'll start with network security, and I won't make it to all four examples, but I'll give you a few examples of how this can be used operationally in some interesting cases. So let's start with network security. And what we did here is kind of trying to take the best that is out there in the analytics domain, take commercial intrusion detection systems, and connect them back to the raw data to allow people to make better decisions. So the basic framework is here. We have an intrusion detection system on this side, and we have the net flow data, which is a raw network data, little aggregated. Net flows are aggregations of the raw IP packet data. And this is basically now coming from the university, and it's basically connecting to the global internet. And so here from the gateway, you get this net flow data. And here you get the intrusion detection alerts. And our system is now in between connecting up this output of the automated algorithms back to the raw data and is helping you to understand these intrusion detection alerts better. So what are the components? And of course, you have to do kind of a number of things here to make this work, because this is a very big pipe of data coming in here. It's billions of records per day, so you can't easily process it. So you have to be aware that you need IP packet stream processing, net flow record aggregation on the fly. So you need special technology even to do that. And you can increase the effectiveness of the intrusion detection alerts by adding something in here. And we are part of a network of honeypots. If you've never heard about honeypots, it's basically computers in the network that you put up just for the purpose of getting bad traffic. They have no other purpose. So there is no valid traffic going to these machines. So everybody accessing these machines is a bad guy. And you can collect information of what they are trying to do. So there is no reason. You just put them out there, simulate something, an open environment, and then people who connect there are usually bad guys that try to infect these machines, try to capture them. And there's a network all over the world of these honeypots that we collect data from together with Symatec. So now, having all that data, what do? We can do net flow summaries, which is basically on the right-hand side, the raw data. You can see what ports have unusual traffic, what is the time development, and so on. You can visualize the IDS summaries, the intrusion detection summaries. And now we put both together in our system that I'm showing you in a second. And then, of course, you can drill down to the raw data, the host details, like every computer, net flow details to do the detailed analysis to confirm what you have found. So now, just to show you a little example here, what is happening here, this is now a complex system for an expert user. So if you don't understand it, it's perfectly normal, because this is the expert user at the administrator's level who is usually dealing with the IDS system. So he's really knowing about IP addresses, sub IP addresses, and so on. And many of the features here are for the expert user. But what I want to explain to you is just the major view here. And you all start with your intrusion detection alarms. And this list is usually too long. So they always work on the top of that list, because you get more alarms all the time. And there are hundreds and thousands of alarms coming in every minute. So you have to basically prioritize what you work on. And that's in general true for intrusion detection systems. So what we can do here is we can now take any part of that list of alarms and then look at the raw data. What is the raw data doing to my network? And what you see here is basically in the background a tree map of your internal network. This is my internal, my company's network, university network, whatever you are looking at. And these are external IP addresses. These little circles is one external IP address that is accessing my internal network and is somehow suspicious. And then we have automated algorithms that are clustering these nodes according to what they do to my network, the behavior of the traffic that they generate. And you see there's a lot of nodes doing very similar stuff to my internal network. And you see that by this edge bundling that they really access a few computers. So guess what this is? This is a distributed attack that is happening every day, at least on the university network. So you have a large number of external machines that are trying to hack one of these machines because they have some open ports. They seem to be vulnerable. And this is what you can easily see by such a visualization. You can drill down and see whether this computer is infected or not. So they are using this at the network administration level to use that. And of course, you have multiple views then to drill down these little timeline views. And these are now IP addresses and ports. So you get the time behavior in these little clocks. And you have other representations that help you to go into your network structure and visualize that. And that's a dynamic system where you can zoom in and out and see certain behavior. You see here, you have this whole subnet. And then you see here the details of the subnet with this node having some interesting traffic at one particular time spot. And this whole thing is set up in an operation controls center where you have basically all the visualizations. And these are high-resolution LCD monitors, each of them having a resolution of 10 megapixel with a touch table, a surface down here that you can control the whole thing. So this is kind of an operational system where you can do this visual analytics in practice. And note, it's combining analytics, the best analytics you can get, intrusion detection system, commercial systems, but connect it back to the raw data and visualize the connected data in a way that you can make sense out of it. And this is big data. This is billions of records that you can access in real time on your backbone, and you need a lot of technology to make it work. But this is one example where really big data is explored by visual analytics means. Second example, customer feedback analysis. And I've no time to go into all the details. So the process of generating, of processing the data is quite a detailed process model. You get basically the input data is commercial data from a big company, all the customer feedback, millions of these little feedback notes that customers write when they have some problem. And I'm sure you had this happen to you. You bought something with some store, and they put up this little box, do you want to give us some feedback? And probably most of the time you click no, but some cases you may click yes and say, this was really bad, whatever I didn't like you put in there. So processing this is basically now the idea here. And no, the big company doesn't have the stuff to read it all. Maybe here in China, but in like the US and Germany, they don't have the stuff to read all these notes that you write. They want to get it aggregated. They want to find the important stuff out of this. And this, of course, they want to find in real time. So this is an idea here. So what do you have to do? And as you can tell here, and I'm not going to explain this because otherwise my time is gone, what you have to do in order to process it. There's lots of NLP that you need to do, like part of speech tagging, whatever, sentiment analysis of these cores, and so on and so forth. So this is the whole pipeline model of what you have to do. Assume that you can do this with a reasonable quality. Now, how can we interact with this? And this is what I'm going to show to you now. The point is, these events, even if you can cluster them, aggregate them, happen at very unusual arrival rates. If you have a problem, you have a big peak coming up of some problem, and you want to detect them. And that's why we come up with a new visual model. Like if you take the raw data, and this is just an artificial example now here, it would arrive at certain positions in time. And here you see I have multiple events occurring at the same time spot. If you linearize them, like just plot all the 5 events that we had here, and this is artificial, what we do then down here is a density curve. This is a density over time. these two events were kind of dense in time, and then there was a gap. That's why it's going down, and then you had a highly dense event coming up here, and so on, and you can calculate the time density. And I don't have time to go into the details, but I want to show you some real examples. This is now real. I have now 27 documents for a certain topic, complaining about whatever topic. And then you have down here now each of the events happening, and red means bad sentiment, green means good sentiment score. So it's quite bad that people were complaining about something, but what you see in the density track, they were highly concentrated at some point in time, right? So you have the linear arrival here, which is not giving you the time, but this is giving you the time, and what you are interested in is not the absolute time, but the relative time, whether it was dense in time or not. So the big gaps you don't see, then it's going down to 0, right? If it's a big gap. But if it's dense in time, so that something happened around this time, right? Something really bad happened. And now we can go in with real examples, and these are now real examples from a real customer feedback stream. And you see here we had some problem happening here, very bad sentiments, very concentrated in time. We have some bad events happening here. And what the system is doing, it's proposing all the topics where there were clusters with interesting co-occurrences of terms that were unusual compared to the past. So you have some values that you know. These things always come, customers are always explaining about certain topics. And what you can do then is also kind of attribute it back to the timeline. This is now the real timeline. These lines give you back the real timeline. And you see these kind of terms that go with these events, and you then can click on every single event and read it if you're not sure what was happening here. And we explored this with the experts that were doing this analysis, and they are more used to it. This is now a timeline where you have all the events happening over time, and you can relate it back. You see a serious problem happening down here. Just two more examples. Packing list example, there was a problem with the packing list. Something went wrong here, and you were able to see that. Customs, something went wrong with customs. Rarely happens, but it did happen. And so we now evaluated this with the real people, and we found all the events that they knew were in that data set, and there was a year worth of data of the customer feedback data. And the more interesting part is we showed them more events, and they evaluated whether they were real events. And they found that we detected more events than they were aware of. So they would love to have known it, but they didn't. So our technique was actually able to help them find more events than they were able to discover with their manual and their means that they had beforehand. And that's a big company doing this. And of course, you can relate it back to geography, positive, negative feedback, overlay it on a map. And you see now here, customer feedback overlap. Shipping seems a big topic always. And you see it's always mixed, negative and positive is mixed. You see here tax exempt was just in some regions a problem, and it's negative. You had some problems due to rain in some regions, which were mostly here. You have some problem that was related to traffic in some regions, and so on and so forth. So you can really do kind of interesting analysis even over the geospatial domain. So this is kind of an example in that domain. And I guess I'm now skipping over the next one because we hear more about high dimension in the next talk, and briefly go into a completely different domain, namely molecular biology, before I conclude. And I think I have 2 more minutes, I guess, in order to do that. So let's go into the domain of molecular biology. And you may have heard about overlapping genes. You may not have heard about it. This is something that is quite new. So you have, and this is just to give you a refresh to understand what I'm talking about, DNA, you've heard about in school, I hope. So these are normal DNA strings. And you have these letters here, and 3 of them make up 1 amino acid. And so you can start at any position to come up with the decoding. And any of them is good. So reading frame 1 is this one. If I start reading one letter later, I get different amino acids, completely different amino acids. And I have 6 reading frames, 3 in the forward direction, 3 in the backward direction. If you read backwards, you get different DNA strings, right? Decoding it in the back direction gives you different strings. So this is standard, right? This is standard knowledge. What is the assumption currently, and most of the DNA analysis is done about, you are taking the most probable of these reading frames. Because biology can take any, right? Reading, you can do backwards, forward, and you can start anywhere you want. So you take the one that is most likely to code a gene or decode a gene. So what biologists have found that in some cases you have something that is sitting in the forward direction. This is coding a gene. And on top of it, and this is now the interesting thing, on top of it you have something in the backward direction. It would be like in a computer program, you code something, and on top of it you have another message coded, which is never happening in computers because there won't be any message. You can't code another program on top of the other, or another, even ASCII text. It's impossible to have another ASCII text on top of another of an existing one. You can try. There will be never anything more than a 3-letter word coming out of it. In biology, they found this to be operational, which means these are long sequences that are sitting on top of each other, and both of them are functional. And this is very surprising. And our project was now detecting that there's a lot more of this happening than the biologists thought there is. And we developed a system that is now helping them to decide which are the candidates of potentially overlapping genes that we haven't known about. And so we developed a quite complex system which is decoding and encoding lots of automated analysis results, and I can't explain it all. It's just to steer your interest in it. That is helping you to decide where there may be additional overlapping genes, and this is expression data that you get, and you see here known genes, and you see potential, and this is a start codon, stop codon frames that you can automatically compute, and then you can basically help them understand where there is maybe another gene that is overlapping with existing genes that you know about. The most interesting part is here we have found that even for the most examined thing, the EHEC bacteria, like the Hefe bacteria, there is about 30% additional genes that are most likely to be overlapping to existing known genes, with their function being not yet known. This is for the most examined bacteria. So there is a lot of additional information encoded here. And the biologists even have more of a problem with our result, because it's very hard to explain how this could come into being, how this could come. You can easily explain how overlapping goes to non-overlapping. You get deduplication, and then you knock out one of the genes, and the thing is functional. But how you get on top of each other, even for computers, we wouldn't know how to do it well. It's an NP-hard problem to put two strings on top of each other encoding, and it's in many cases not possible. Here we have it happening almost everywhere, and we don't know how this could be encoded. So this is kind of a problem. They have no models yet. Actually, the biologists have a problem. Luckily, I don't have the problem. They have to find the solution here. But the results are very surprising to them, so there is quite some resistance in the biology domain. Some people say that it can't be true. They simply, but it's all made on based on this automated analysis, and our biologists do wet lab experiments to confirm that they are functional. So they have shown for some of them, and this is difficult to do, of course, but it's possible these days with all their kind of creating stop codons into sequences and so on and so forth. So they can really prove that some of them are functional. So it is there. It is true. Everything is confirmed so far as we can tell, but it's an interesting result. Okay, with that I would like to conclude. What are the perspectives? And I could go on. We need a lot of additional things. We need a methodology to define what are visual analytics problems. We need to understand what the data and the task is, including all the big data parameters like volume, variety, velocity, veracity, and so on. Then we have to decide, in going about to solve a visual analytics problem, can we solve the problem fully automatically? It may be possible. Then it's not a visual analytics problem. If you can solve it fully automatically, I would propose to you use the automated methods to do it. There is no need to bring the human in. But if it's not, we have to decide what can be done, what must be done automatically, and we kind of need to provide the best support to the user to solve his tasks. We need to define the workflow of analytics and visualization, and then we have to decide on how to visualize it and how to do it best. And of course, in the end, we have to implement it. So if we follow these steps, it's actually the steps that I propose to my PhD students when they have to deal with a real-world problem in kind of deciding how to do it. And when they find out here it's a yes, then they stop. I tell them, don't go further, it doesn't make sense, right? And they have to basically go through all this process to do it. So there are interesting aspects how to do it, the implementation, and there are commercial systems out there that help you. And they range from a loose coupling to a tight coupling, and I could name now the companies that go with it, but there is very little on the tight integration level. There is basically none of the products that you can buy is doing a tight integration, so there is lots of room for research to help to do here better in this domain. We need this tight integration to solve the problems. And of course, we want a high flexibility with the least possible programming effort, and there's no system currently out there that does it. So with that, I would like to conclude, and thank you for your attention. Are there any questions?
Thank you, Professor Kim, and very interesting talk. And I'd like to ask about the question about the cybersecurity visual analytics, as we already have a lot of the automatic method for detecting the network events. So which part do you think is most needed or critical for visual analytics do for the cybersecurity, so that the automatically cannot be done individually?
So, like we are working in an EU project together with Symatec and other companies that kind of are really working on this. So what we have learned is they can do great stuff in creating alerts, potential events that may be suspicious, but they can't decide finally between a new computer game causing that traffic or a new virus causing the traffic. This decision is still up to the human, because it involves general knowledge that the computer doesn't have. You can't explain to him, you can't have the computer check automatically whether it's a game or not. So these things are very hard to do automatically. And that's just one case. And in case of all these fraud things, there is a human intelligence on the other side. And you never know what the human intelligence is putting in. Because they try to basically get around everything you do in your automated system, they exactly counterbalance that. Like if you put thresholds on the number of accesses to a computer, like for distributed attack, put that threshold to 50, you'll see the next day all these distributed attacks go in with 48 or something, right? If you change it to 45, your threshold, they come in the next day with 43. So there's a game, right? It's a game going on between intelligent humans, and you can't compete with the computer. You can't do it without the computer. I'm not saying you should get rid of the computer, but you need the computer and the human to make these decisions on what to do. And this is where I see the need, because there's intelligence on the other side. There's human intelligence, and you can't counterbalance this just by computers. There's always a human making the final decision. Also in fraud, the same thing.
Hi, I'm Zu Chao Wang from Peking University. Your talk is nice, and I want to. I'm actually doing visual analytics, and I like the idea of tightly incorporating computational analysis and interactive visualization. But I find latency and speed is always a problem. For example, for visualization, if it's slow, you can always aggregate or analysis, and you visualize the result. But if the analysis is slow, especially for big data, what is the solution? Thank you.
Yeah, so scalability is of course a problem, especially in the network domain. It is certainly a problem, but in many other cases as well. And of course there is not a simple answer to this question. You need to take many of the currently available methods and like techniques like Hadoop clusters and whatever, you need to take that into account. So we have like the student actually worked a year on the data side before he did any visual exploration of the data. Just to load the data, this NetFlow data, into our database system and do all the pre-aggregations, and he was getting it down to 5-minute intervals. So real time in that case means 5 minutes after the fact. That's what we were able to get. Of course, you can do better if you put more resources out, right? But it's a challenge because the data is increasing, right? And there are methods out there, stream processing methods and so on and so forth, that you need to build in, otherwise you have no chance. But I think this is orthogonal to a certain extent to what we do, right? There's some people in the database domain working on this, like AT&T people have worked on scalable aggregations with guarantees. So you do basically not fully correct aggregation, but you have guarantees on your aggregation. So they can do it at any time frame with the best possible error rate. So we probably have to work and take some of these technologies and incorporate them.
Good afternoon. I'm at the side of the room, and I have two questions. First is that in this talk, I heard that nearly each of your projects are heavily involved with domain experts, right? And I want to know that if there some good experience to share with us that how to cooperate with domain experts or to better involve them into our projects.
Yeah, that's actually key to what we do. And if you want to, like the title of my talk was solving problems. If you want to solve real world problems, you have to work with domain experts. No way without that. And this may be taking quite some investment of your time and energy. And in some cases, it may not lead to anything because some of these projects, they walk away, they don't take the time that would be needed. So if you want to do relevant work to some people, you have to be willing to start a year of work without knowing any direct outcome within that year. And that's, I guess, my experience. It worked quite nice in some cases, but I can guarantee you that you will have some failures. If you don't want to take that risk, then don't do it. Then work on some theoretical problem and abstract it out. But if you want to have an impact and solve real problems, you have to be willing to invest that. You won't be otherwise do relevant work to these people and solve their problems, right? If you want to solve a problem in molecular biology, you have to become partly an expert. And I've learned a lot myself. I've learned a lot about molecular biology. My student has learned even more. She knows now things that I don't know, right? Network security, my students are experts on that. I'm learning myself a lot. Linguistics, we have worked a lot with linguists. I'm learning a lot about languages, but my student, he's now sitting together every day with these people and is an expert in linguistics now. He's publishing more in linguistics conferences these days. So it's like, yeah, so you have to be willing to do that in order to have real impact, I believe. And visual analytics is a highly interdisciplinary field. I don't think we'll have an impact if we are not willing to collaborate. That's a very simple story. It takes an investment, but it makes your work very much relevant. And if you see people in these domains using it, that makes it a lot nicer, right? If you see that they deploy it on an everyday basis and it helps them in their work and solves new problems or brings up new questions that they have never thought of. This is fun. I like it if they are puzzled and I tell them something and they, this shakes our world, right? This is changing our, like I could have shown some examples from linguistics, and these people were kind of astonished at what the outcome were, because we were dealing with languages that we have never, I don't know anything about. And we were able to show something on vowel harmony in these languages without knowing anything about these languages. And they were confirming it after going back to the library for a week. And they said, oh, you could do that without knowing anything? This is like showing the potential of visual analytics and it making a very convincing case. Since they discovered that, they were very willing to work with us. Right? So it's like if you have these successes, then these people are very, very open, and then it's a lot easier. But it takes maybe a year to start. Yeah. So sorry, no good news on that side. But you have to be willing to invest, and then it may be very beneficial for both sides.
Due to the time limit, we do not pick up the further question. Any interested audience could talk with Daniel offline. Let's thank Daniel again for this great talk.